Okay, today it's my pleasure to introduce our very eminent alumnus, Professor Yan, Tung-Mow Yan, to give the talk a very prominent title, because this year is the 50 years of Quarks, and also to add to that, I'm sure he's going to touch on it, 40 years of Quarkonia. Professor Yan graduated from NTU as undergrad in 1960. And remarkably, he did a master's thesis at NTU before leaving for the US to Harvard, becoming a student of Schringer. So I was just chatting with Inami-san, saying that then he went to SLAC and worked on the Parton model Drell-Yan process, this most famous process producing many Nobel Prizes. But if he stayed on the East Coast, probably could not work on this because of the Parton model, right? And since 1970, he went to Cornell as faculty and rose through the ranks, including becoming an emeritus in 2010, right? In between, he visited SLAC and CERN, and also as a distinguished professor, visiting professor at NTU in the 80s, and also around 90 or so to Academia Sinica, which he made quite a lot of impact because of the heavy quark symmetry at that development at that time. Excuse me. He has been a Sloan Foundation Fellow and also an APS Fellow. I guess besides the Drell-Yan process, he was also part of the Cornell Potential Group. So two very strong impact works on issues related to the talk today. So, Professor Yan, we're glad to have you back on this very prominent occasion and on 50 years of Quark.
Yeah, it works. Thank you for the invitation to give a seminar here. The title of my talk is 50 Years of Quarks. And this year, as George just mentioned, marked the 50th anniversary of the birth of quark model in 1964. And this is my, before I go on, I would like to say, I will give a very informal and qualitative talk today. There will be no complicated equations. There will be no citation of many people. In case your work is not mentioned, I apologize. And also, I'm sure you will not learn anything new from my talk. So why do I give this talk? Well, the reason is to show you the frontiers of physics 40, 50 years ago were much easier than today's frontier physics like LHC and the string theory. I mean, all you need from here, you will see just the elementary quantum mechanics, first year quantum field theory, nothing else. So I have very great respect and admiration for the new postdoc and young scientist physics, because in terms of investment, you have put in lots of effort into it, but the return is uncertain. In terms of the stock market jargon, the PE ratio is just too high. Okay, so this is my the outline of my seminars, and I will start with the SU3 flavor symmetry in 1961, light quarks and SU3 colors, Parton model and quarks in 68, and then I'll talk about the year 1974, because many very important events occurred during that year. And then I'll start talking about heavy quarks. In fact, my involvement with quark started in 1964 4. I did not do any work on light quarks before, and only work on heavy quarks. And then I'll show you some qualitative reasoning, and then you can get lots of predictions for harmonic. And then I'll mention Cornell model, Epsilon family, hadronic transitions between heavy quark states, and then I'll talk about heavy quark symmetry and chirodynamics. Okay? So let's begin. So the light quarks, in the late 1950s and the early 60s, many particles were discovered, and Kellman and Neiman independently noticed that if you use the SU3 group to classify the particle representation, then all the known hadrons will belong to the octet or octocouple. For example, how do I do this?
It's funny.
Oh, and then mix it. Does it work? Oh, face this one. For example, the spin zero pseudoscalars, pi, k, and etas belong to the octet. And then the spin 1 vector mesons, rho omega phi, and k stars also correspond to the octet. Then the spin 1 half baryons are also represented by octet, and the spin 3 half baryons are represented in this decouplet. And this particle, omega minus, was missing when the A4 way was proposed, and it was discovered. This particle was discovered in 1964, and I was a second-year graduate student at Harvard at the time, and I still remember how excited people were about this discovery. Now the SU3 is a round 2 group, so there are 2 quantum numbers, and one is the third component of isospin I3. The other one is called hypercharge Y, is S equal to plus B. And in this graph, the horizontal axis correspond to S3, I3, and the vertical axis correspond to hypercharge. And this group is very successful in representing this hadron mesons and baryons. But there's one puzzle, namely that the simplest representation, triplet or anti-triplet, are not represented by any particles. This is as if you discover the angular momentum, but somehow the spin 1 half doesn't exist in nature. So this is a big puzzle to theorists and many others, especially to Kellman. So in 1964, again, and this shows that a good idea always happens to many people simultaneously. So Kellman and Zweig noticed that if you propose the existence of 3 spin 1 half fractional charge particles called in quark, up quark, down quark, and strange quark, and electric charge 3 halves are 2/3, minus 1/3, minus 1/3. Then this will form the missing triplet representation I mentioned, and then all the mesons can be described as a bound states of quark anti-quark pair, and the baryons will be bound states of 3 quarks. So instead of many representations, what you need are 3 spin 1 half charged particles, from which you can construct all this representation. It's like a periodic table in the chemistry. All you need is the nucleons and the electrons. You can build up all the different elements, and the same thing here. Okay? But the question is, are they real or fictitious? This the fractional charge particle, especially after a long run. Many searches for these particles without success. If you read the Kelman's original papers about quarks, then you'll find that he is ambivalent. Some cases he will say they could be real, some cases they need not be real. And so he seems to be, on both sides. And of course, if you discover he will get the credit. If they are not discovered, he said, well, I told you, they are not real. So it's a very clever maneuver. Unfortunately, I never read the Quarks paper. The paper was not, he had two papers, and existed as certain preprints. And before the seminar, I was talking to George, and apparently Quarks wanted to submit his papers to physical review letters, but the CERN's authority said no, you have to publish in the European journal. So he decided not to publish at all. So I really don't know what he said in his papers. All I know was the CERN preprint number quoted by many people. I just copied from them, so I never read it. There's one fatal flaw, I call it, and the reason is that if you remember, this, for example, the spin 3-half baryons. The spin 3 charge on spin half to form spin 3 halves. The spin wave function are totally symmetric, and then this is the lowest energy state, so they don't have relative angular momentum, so they are relative S states. So the spatial wave functions are also symmetric. So somehow the overall wave function is symmetric with respect to exchange of two fermions. So somehow they have to satisfy the Bose statistics. And this problem was solved in 1964 with the introduction of the new quantum number color. As you know, at the time the color was only purpose was to solve this spin statistical problem, but did not play a big role in the classification of the spectroscopy and so on.
The year is
Not quite right?
far from correct.
What year?
In 1964, of course, nobody knew about the statistics problem.
No, it did. You check the paper by Weinberg or Hannah Moore.
No, it's, I think later than this, but.
No, they may not call it a color, but it's a new quantum number.
Yeah, but you say SU3 color, and
Oh,
One
yeah.
and Fish would claim that's their
Yeah.
picture.
No, I apologize, I was too sloppy. Yeah, there's a quantum number here. And each quark comes with 3 colors, and then turns out that all hadrons are color singles. Now this SU3 color, later in the 1963, when the asymptotic freedom and QCD were discovered, then play a very crucial role in understanding the hadron strong interactions. Okay? Then came in 1968, the so-called deep inelastic electron neutrino scatter. Now Feynman's famous Parto model was a way to explain these experiments. And then Feynman wanted to make sure that quarks are not the only choice, could be something else. That's why you call partons, not quarks. But you know the theories jumped the gun quickly and then insisted the partons are quarks. And of course at that time there was no gluons because QCD was not there yet. But anyway, if you identify partons with quarks, then you can apply to electron and neutrino scattering, and it led to many predictions, and they all agree. Furthermore, they also found that the total momentum fraction carried by the quarks doesn't account for the total momentum of the proton or neutron. And then of course we knew later that those are the momentum carried by gluons. Okay, so in this Tung-Mow model with the quarks as protons, a nucleon will have 3 quarks called valence quarks. Now we are using the language of chemistry. This carry a common number nucleons. But then the Q bar pairs, they call it C, okay? And I think this is the first dynamic application of quarks. It's after deep inelastic electron scattering, people started to feel that the quarks are real, okay? And then of course, after QCD and symptomatic freedom in 1973, then many more predictions were found, okay? Now I come to the heavy quark or heavy quantum state. Now the year 1974 is a very important year. I will mention a few important events which happened in that year. One is the ratio of E plus E minus going to hadrons divided by the corresponding cross-section for E plus E minus to mu pairs. Now this ratio can be computed in Tung-Mow, and it's a constant. But in 1974, there was an accelerator center called Cambridge Electron Accelerator. It's operated by MIT and Harvard. And that year, they decided to shut down in 1974. And before the shutdown, they measured this ratio. And this ratio is rising with energy, with a huge error bars. But you still can see the trend is rising with energy. So people was wondering why these ratio R keep rising. Okay, that's one important question. The other one is the London conference in 1974. I was there. Ken Wilson was there also. And then one of the key questions was when the charm will be discovered. You will remember the charm was proposed by Glasgow and Bill Ken to form a symmetry argument because you have up quark and down quark. You have charm, you have S quark, but without a corresponding 2/3 charge quark. So they proposed an additional quark. I don't know if they call it charm, but anyway, this is the additional quark that Glasgow and Bill Ken proposed for symmetry reasons. But more important, Glasgow, the gym mechanism. I could not pronounce this Greek, Italian name, gym, I-N. Anyway, the gym mechanism is a way to propose to suppress the flavor changing neutral current. They show that if you just have 3 quarks, up quark, down quark, and strange quark, there will be a huge flavor changing neutral current and in violation with the experiment. So they show that if you introduce additional charge 2/3 charm quark, then you can suppress those flavor changing neutral current, okay? So, and then Ben Lee and Mary Kay Kaya also just published a paper, or there's a preprint, I don't know if it's published or not. Give a very comprehensive discussion of the phenomenology of charm mesons if they were discovered. So in 1974, people were asking when would they be actually discovered. Now, Ken Wilson, I believe Ken Wilson at the London conference proposed the following, that this rising cross-section actually was due to the opening up of the charm quantum number. And then he further suggested that if the heavy quark, the charm quark is about 1.5 GeV is heavy compared with all the other quarks, then the bound state will be small because the mass is heavy, And then according to asymptotic freedom, the coupling between them will be weak. Then he said that in analogy with the positonium, then there will be bound states just below the chance ratio, like a positonium. So in the summer of 1974, lots of people discussed Ken Wilson's proposal and so on. And then the Appelkers and the Paulison, they worked on this suggestion at Aspen. And then after the summer, then November revolution happened. Probably most of you are too young to know. But Jeb Psi was discovered in 1 week. And then a week later, Psi prime was discovered. So after the 1 week, I got a phone call from Citron, said, we found another one. I said, which another one? He said, well, there's another particle, Psi prime, called discovered. Now you probably know the story about the GM Psi. 17 has an experiment at Brookhaven, look at the new pair of production from a PP collision. And they found something unusual, and they could not explain it. And he was sure there must be some systematic error in their analysis. But you know, something always assigned two independent groups to do the analysis. Only he himself has access to all the data. And he wasn't sure what to make of it. And then he was visiting the SLAC. And the SLAC also was puzzled by a scan with some huge peak, and they were not sure what they were either. And so when Santin and the SLAC people talk to each other, they realize they're talking about the same thing. So that's what they discovered. Now, they published the papers back to back in Physical Review Letters. And that started the whole Cornell states. And this is my beginning of the involvement with heavy quarks. Now at Cornell we have a group of people, Godfrey, Akron, Kinoshita, Kenan, and me. John Cocker was involved in the first paper, but then he left the group afterwards. Okay? So let me, this is 1974. So let's imagine this is December in 1974. And we were given the following experimental information. We know the mass of Jeb Psi. We know it's decay to E plus E minus width. We know the Psi prime mass, the electron E plus E minus width. And then we also know Psi prime goes to J Psi plus 2 pi at a huge branching ratio. And then we have never width. J Psi is about 100 keV, and the Psi prime is about 300 keV. Now to impress you how narrow these states are, let me introduce the dimensionless parameter, the width over the mass. And then for ordinary hadrons, you will find that this ratio is about 0.01 to 0.1. But for J, these two narrow states, this coefficient may be off by a factor 2. But anyway, it's order 10 to the 5th. So it's very, very small compared with the other typical hadrons. At the time, the simple explanation is that if these states are above the threshold, say charm quantum numbers, then this charm quark can come out in the final states. And so there will be no, they just can break up and to combine with the quark anti-quark pair created from the vacuum. And since the light quarks are very light, it's very easy to create these pairs in the vacuum. And so this width will be big, and that will be ordinary hadrons. If this stage is below the charm, anti-charm threshold, then this charm quark cannot come out. So they have to annihilate first, and then because these quark states are very heavy and the gluon couplings is small, this width will be small. So that's, don't take too quantitative, but that's a simple qualitative way to explain why the widths are so small. Now, from this D, psi prime going to psi plus 2 pi, we can, the natural explanation is that these two states are different states of the same system. So they're very similar. Right? So this will be interpreted as CC bar upon states. And then we will assume that it can be described by a non-relativistic Hamiltonian, p squared over 2m plus v. Why can we do that? Well, because the mass difference between the two states, psi and psi prime, is only 600 MeV. It's very smaller compared with the mass. So the excitation energy is small compared with the mass itself. So the system probably is non-relativistic. Then we have the number for the electronic width. There's a psi going to E plus E minus, or psi prime going to E plus E minus. And this is given, but this width is given through annihilation of the CZ bar quark. So given by this formula, well-known formula. Okay? And then you can see that depends on the wave function at the origin. Because for the two quarks to annihilate, they must meet at the origin. And so the only states which will be seen in the E plus E minus channel is states with non-zero wave function at the origin. And those states are the zero orbital angular momentum states, okay? So so-called S states. And then there must be spin triplet. Why? Because they decay through E plus E minus, going through virtual photon and then decay into E plus E minus. And then we know that the photon carries spin 1. So this must be a spin triplet, spin 1. So from this, we can deduce the wave function at the origin of the excited state over the going states 0.62, okay? Now, it turns out this number is sensitive to the potential. If it's a Coulomb potential, this ratio is 1 over 8. If it's a linear potential, this ratio is 1. If it's a harmonic oscillator, eta is 1.5. So this number, 0.62, is between the two potentials, Coulomb and harmonic. So from here, we can do a very simple extrapolation. So let's take 3 potentials: Coulomb potential, oscillator potential, and then this potential we don't know what it is. And then fix the energy difference between the first excited state 2s and 1s, because those are the observed psi prime and psi. So this is 3.7, and that is 3.1, okay? Now, I mean, the P state, the first L equal to 1 state, is exactly halfway between these two states for harmonic oscillator. And then for the hydrogen atom, for Coulomb potential, the 2s states, it's much closer to the second S state than the first S state. So the hadron, the first P state, must be between this one and that one. So it will be closer to 2s, further away from the 1s. And the mass difference is 600 MeV. So one can guess that the ratio probably 200 or 300 MeV. So right away, we will guess that there will be a P multiplied this L equal to 1 states at this energy range 3.4 or 3.5.